The Kepler telescope discovered an Earth-like confirmed exoplanet called Kepler 443b. This exoplanet was discovered by Guillermo Torres on January 7, 2015. It was found using the transit method, a method that determines the exoplanet's radius by observing the light of the parent star's disk. The parent star, also named Kepler 443, is about 2,541 light-years away from our Earth and has a temperature of 4,723 kelvins. This parent star is also about 26% less massive than our Sun and is about 3.2 billion years old. The radius of Kepler 443 is also about 30% less than our Sun. This star has an apparent magnitude or visibility from Earth of 16.2 and an absolute magnitude of 6.7. In this solar system, there is only one planet, Kepler 443b. The mass of Kepler 443b is 0.0182 times that of Jupiter and 5.797 times that of our Earth. Kepler 443b has a Jupiter radius of 0.208 and an Earth radius of 2.33, meaning its radius is 2.33 times greater than that of Earth's radius, which is about 3,959 miles, or 6,371 kilometers. The orbital period of Kepler 443b is 177.669 Earth days, or about 1/2 the average full Earth rotation. Kepler 443b falls into the habitable zone, as shown by the image, where the red dot represents the star, Kepler 443. This is where Kepler 443b is located on the stellar map. This is a zoomed-in version of the stellar map, showing Kepler 443b's location. The orbital distance of Kepler 443b, or the circumference of the orbit, is approximately 0.49 astronomical units, which is equivalent to 7,405,946 kilometers. For reference, the inner boundary of the habitable zone in this solar system is 0.342 astronomical units, and the outer boundary is 0.719 astronomical units. Kepler 443b's eccentricity is 0.11, which is how much the orbit of an object deviates from a perfect circle, with a perfect circle being 0. In this situation, the only thing we can calculate is orbital velocity. To calculate this equation, we first need to derive it from force unbalanced equals mass times acceleration. In this case, it is radial acceleration, so the force unbalanced is equal to mass multiplied by velocity squared over radius. The next equation we have is the force is equal to the gravitational constant, the mass of one object plus the mass of another, over the radius squared. Using substitution, we can set these two equations equal to each other. One of the masses cancel out, leaving just the mass of the planet, and then one radius cancels out, leaving just one radius. This leaves the final equation, v squared equals the gravitational constant times the mass of the planet over the radius. We plug all of these numbers into the equation and finally get an orbital velocity of about 400 million meters per second.